Hello, my name is Tom Chatterton. I'm the Ohio Chapter webmaster. This is our website over here. I have on the website some things here. We'll be able to look at that later. I want to see if there's a thing where here will let me go to the slides and the pen. I don't see the pen. Here's the pen. I'm not used to 2007. We're going to go ahead and get a felt tip pen, and we're going to pick a color real quick, even though we're not. Give it to that. I'm going to pick magenta. This one looks good. Okay, let's go to the next slide. My mom said, never to brag, but our purpose today is to present real-world solutions to present drinkable water to a future growing Mars colony, plus an expanding manufacturing base. Okay, why do I have qualifications to discuss this subject? I'm a retired Class 4 water plant operator from northern Kentucky whose career spanned from 1979 to the early 1990s. I received a Class 4, which was the highest achievable in the country in 1990. I don't know if it's been changed since then. Of course, then I did some computer field technician in Y2K. We all know where that went, so I ended up in massage therapy in California. And I bring a wide range of experience and knowledge to the discussion, and of course, this was our introduction. Okay, water on Mars is very significant. My theory is we needn't worry. We'll find fresh water sources all over Mars, and the permafrost in caves, perhaps, and we can use traditional water treatments like we use on Earth. Where there is H2, it doesn't look like it clears like it does on mine at home, by the way. We're going to find about 50% water in some of these regions, especially in the southern regions and on the poles. So we're going to show you how full-size water plants operate, and I'm going to do a summation, and please excuse if I rush, and we can have some question and answers. I don't know, we're running kind of short. So anyway, like your relatives showing your favorite slides, I have about 30 of them, so please bear with me. And here's the big one. Let's see if it comes in. I'm going to have to use, let's see if it's cooperating. This is a different version of it. There it is. Oh, it went up. Okay, it's delayed. I think Earth's first trillionaires may get their money from colonizing Mars. Here's our money pot right there. Okay, water on Mars. To process water by my methods, we need lots of water. So first, let's talk about how much water there is. NASA confirms there's water, and wherever there's water, there can be human progress. You know, civilizations have expanded from sources of water and trade. It would be the same for Mars. And there's a delay. Okay. And it's trying to get away from me there. Okay, we're going to use the pen if I still have it. My favorite place to land is right up here. I think there's some iron sulfates up here we're going to need for processing water, some iron sulfates up here. And there's a big catch of iron sulfate in here. Zubrin wants a city right here, by the way. Right there, I'm marking that off in that area, right up next to some hills, overlooking the Val Marinar. Nice view for all the rich people that are going to be living in Zubrin City right there. Okay, now we're going to put a train from the pole, and we're going to run around these mountains here and go up here into our first settlement and then over to Zubrin City. And we're going to put another one up here, down into here. These are 3 volcanoes. There's a lot of volcanic ash here. This is the big one, this is Val Marinar. This is Olympus Mons. There's a lot of ash here from the lava going into where this ocean used to be. And this is similar to Napa Valley in California, which is also a lava bed. So we're going to be able to grow grapes up in here. I know it's a big mess there, but let's see if we can clear that, and I won't draw on it. Just a second. Oh, it came back. I guess it has a memory. Anyway, just to play around here and have a little bit of fun with you. Recent signs of liquid water on H2O. This is actually a drawing. It's not an actual photograph. But then we sent NASA over to take a closer look and see why the water's liquid, and this little guy showed up. And, of course, they went back about 15 minutes later. So, anyway, you can watch that while I try and see if I can get to the underneath here. Which one is the underneath where I can start some multimedia? Every laptop seems to be different. Let's see if I can get up underneath this. This is why we are going to be processing Mars. Oh, he doesn't have one for that. He doesn't have a Windows button. Okay, we'll come back to this slide. I can do that. I found the place to go there. So what I'm going to do is I'm going to go ahead and see if I can find my... do you want to keep your ink? Keep. Okay. What we're going to do is we're going to go down here and we're going to start a voice presentation. This one. You can go ahead and listen to this for 4 minutes, 55 seconds.
Presented by Science and NASA. Instruments on board NASA's Mars Odyssey spacecraft have revealed more underground ice on the red planet than scientists expected. May 28, 2002. Using instruments on NASA's 2001 Mars Odyssey spacecraft, surprise scientists found enormous quantities of buried treasure lying just under the surface of Mars. Enough water ice to fill Lake Michigan twice over, and that may be only the tip of the iceberg. This is really amazing, says William Boyd from the University of Arizona. This is the best direct evidence we have of subsurface water ice on Mars. Indeed, he says, what we have found is much more ice than we ever expected. Boyd is the principal investigator for a suite of instruments on board Odyssey, collectively known as the Gamma Ray Spectrometer, or GRS. The GRS has been mapping Mars since February 2002 and has detected telltale signs of water ice in the upper meter.
A lot of noise. Get to those two first.
It may be better to characterize this layer as dirty ice rather than as dirt containing ice at that point. The amount of hydrogen detected corresponds to 20% to 50% ice by mass in the lower layer. Because rock has a greater density than ice, this amount is more than 50% water ice by volume. This means that if one heated a full bucket of this ice-rich polar soil, it would result in more than half a bucket of liquid water. How does the GRS detect water from Mars orbit? When cosmic rays from space hit the Martian surface, gamma rays and neutrons fly out of the soil. The GRS can detect those gamma rays and neutrons and measure their energies. Such data reveals to scientists what elements are present in the soil. Researchers are particularly interested in hydrogen, a telltale sign of H2O. Because hydrogen is most likely present in the form of water ice, the GRS can measure the amount of permanent ground ice and how it changes with seasons.
I could get to these two.
The instruments that make up the gamma ray spectrometer can sense the composition below the surface to a depth as great as 1 meter. By combining the different...
Yeah, I couldn't get the speaker. I couldn't get the sound up. That's why I brought the speakers. Well, we...
much more concentrated in a lower layer beneath the topmost surface. The team also found that the hydrogen-rich regions are located in areas that are known to be very cold and where ice should be stable. This relationship between high hydrogen content with regions of predicted ice stability led the team to conclude that the hydrogen is, in fact, in the form of ice. The ice-rich layer is about 60 centimeters or 2 feet below the surface at 60 degrees south latitude and gets to within about 30 centimeters or 1 foot of the surface at 75 degrees south latitude. William Feldman, principal investigator for GRS's neutron spectrometer at Los Alamos National Laboratory, notes that the signature of buried hydrogen seen in the south polar area is also seen in the north, but not in areas close to the pole. That's because north polar regions are now covered by a seasonal layer of carbon dioxide frost. As northern spring approaches, the latest neutron data indicate that the frost is receding, revealing hydrogen-rich soil below. We have suspected for some time that Mars once had large amounts of water near the surface, says Jim Garvin, Mars program scientist at NASA headquarters. But where did all that water go, and what are the implications for life on Mars? Measuring and mapping the icy soils in the polar regions of Mars, as the Odyssey team has done, is an important piece of this puzzle. But we need to continue searching, says Garvin, perhaps much deeper underground for what happened to the rest of the water we think Mars once had. Another new result from the neutron data is that large areas of Mars at low to mid-latitudes contain slightly enhanced amounts of hydrogen, equivalent to several percent water by mass. Interpretation of this finding is ongoing, but the team's preliminary hypothesis is that this relatively small amount of hydrogen is more likely to be chemically bound to the minerals in the soil than to be in the form of water ice. Mars has surprised us again, says Stephen Saunders, Odyssey's
jet propulsion. Results from the gamma-ray spectrometry team are better than we ever expected. This story is based on a NASA press release and read by Tony Phillips. It's presented by Science at NASA and the NASA Marshall Space Flight Center. To find more Science at NASA stories on the internet, please visit science.nasa.gov.
Oh, good, it stopped. Looks like it did. We'll go ahead and eliminate that one so I won't restart that one. This is a little bit different than the one I'm using. I'm using the 2000, and it clears it when I do mine. I don't know why they changed that. We'll go through all this to the next slide. This is about polar water trains. I had these little points up here, and we could be feeding polar water ice up here. I have an idea for a train. Also, there's an incredible hydroelectric power here beyond our technology to process, but we have to get to the drinking water. Okay, this is what Terraform Mars looks like. I have a music composition I could start later. Okay, the one way to process water is to use iron sulfate. It's the cheapest, lowest cost. We can call it the Chatterton method. First, we need a technician. We could have used alum, but there's a problem with Alzheimer's and so forth. They're worried about aluminum, so we're going to use iron sulfate. And there's plenty of it up there. We have, for pH control, you're going to use lime, chlorine disinfection reaction. Lye is okay, but it has a tendency to freeze at around 50 degrees Fahrenheit at the 50% solution, so we might have a problem with that on Mars. We're going to need sand, electric motors, sediment basins, filters, air compressors, water mains, fully tech biolab, and we'll just go to the next screen. That was about the sodium hydroxide. What did I say? Aluminum sulfate has worked for hundreds of years clearing water. And everyone's saying that we know of never took notice. And there's a problem with the Alzheimer's and so forth, so we're going to be using iron sulfate. And since the 80s, they've been gradually moving away from the aluminum sulfate. This is where we're going to find iron sulfate. It's a big catch over here. You can see the colors. Actually, it's yellow over here. This is green, so it's manageable here. And right here where I want to land, right above Zubrin City here, within 100 miles or so, I don't know how long that is, 150 miles maybe. In this area, we can do our hydroelectric, and we can do our settlement, and we can get the iron sulfate to process the drinking water, and we can take it and throw it over the cliff to get some hydroelectric. This is a Petri dish. This checks for E. coli. This is all the stuff that we would put into our lab. I think some of you probably have some lab experience maybe, either in college or high school. So we're going to need Petri dishes, pre-treated with agar, permissible vacuum equipment to suck the water down through the filter to, get the E. coli, if there is any, to stick to that. We want to check for E. coli because we do have humans in the area, so we don't want to spread any disease in the water. And arsenic is for testing for iron. We don't want to do this very often because arsenic is poison. It's very risky for the operator. Make sure your hands are clean, things like that. Use plastic gloves when you make that test. We're going to need a microscope because we are going to have to check for microbes, and we're going to need a chlorine tester. Standard lab equipment not mentioned. Okay, let's run through some chemistry. Okay, this guy right here. We have a large population on Mars. We're going to have to check for pharmaceuticals and hormones in the water. I don't think we're going to be worried about that right away, but as the population goes up, you also have to check for pharmaceuticals. Okay? Every day we're going to need to check alkalinity, color, water, pH, taste and color. These are two, it doesn't do it anymore, but we need to test for these and heavy metals, salts. Here's the E. coli again. I've got that up there. Also, we might have some organic matter, probably from regenerated water. Sometimes we might have to check for that. Well, we might have a concern with radon gas on Mars as well as it is on Earth. There's the heavy metals, and let's go down here. I'll load these up real quick. You have to check pH every hour. I want it to stay around 7.6. We want to check for temperature and taste. We probably want it around 15 degrees centigrade for taste, and comfort to the palate and everything like that. And then suspended solids, which are different than turbidity. Turbidity is when you look at a swimming pool and you see the water's cloudy. There's you want to keep this under 1, and you want to keep this under 1. Your suspended solids, when it's there's mud in the Ohio River, it can go to like 300. So we want to keep this under about 1. And then 1.8 is the ideal.